So comprehension. Your routing algorithm should understand and analyze the available information about the current network status and provide an up-to-date picture for subsequent situational awareness levels. So for example, synthesize the location and direction and velocities of two vehicles relative to each other. So in that first level, in the earlier perception level, what you're gathering is these basic safety messages, and they're telling you the velocity and position of individual vehicles. Now in the comprehension level, you're saying, what does this mean for communication between two specific vehicles? In other words, if you know the individual vehicle's velocity and direction, what does this mean for their relative movement? Because obviously if they're both going forward at the same speed, the actual link distance stays the same, doesn't it?
There is no double effect in this case.
Yeah, exactly. So we have to synthesize that information from these basic safety messages to get the relative movement of vehicles. Are they moving towards each other, away from each other? What's their relative speed? Now, projection. In order to do this routing, we know for a fact that you've actually then got to use this information to forecast the future status of the network. Predict the link lifetime. This is the connection time between particular vehicles. And look at its reliability value based on the synthesized information. In this respect, projection tries to answer the basic question: how reliable is a particular communications link between two vehicles, and when is this link likely to fail? Now, resolution is about the actions needed to require a route between a vehicle sending to another vehicle where the communication hops between vehicles in the event that a particular link fails. Okay? So trying to get two vehicles to talk to each other. What happens when a particular link fails? You need an alternative route available. And this task can be accomplished by considering multiple disjoint routes between the two vehicles, the source and the destination. Now, we do, our papers do tend to be very technical, so what I'm trying to do is get across the essay concepts we use. So, identifying feasible routes in a multi-hop vehicular network, subject to multiple quality of service constraints, is in fact a multi-constrained optimal path problem, which is NP hard if the constraints are mutually independent. Now all that mouthful means is, if we try and solve the problem by what we call exhaustive search, trying every possibility, if the problem gets to a decent size, we can't solve it. Okay? Right. Now, when we talk about quality of service constraints, why do they come in? It does matter what kind of message you're trying to send. If it's text message type stuff, it doesn't have to arrive in a particularly nice, smooth fashion. But if you're sending video from example, should we say, a police vehicle to an ambulance that's coming up the road to arrive at the scene, and they want to know what they're coming to, that needs to be of good quality in order to be usable. And so you need nice, steady transmission of packets. Now, what we've actually done, again, is borrow from nature. Ants are very good at leaving trails, using something called pheromones to guide ants that follow them. Okay? And so famously, this technique's called ant colony optimization. Now, we use ideas from ant colony optimization, but vehicular networks are so fast changing on real roads that if you try and look for the perfect optimal path, you're not going to get very far. So what we do is we use the ants to find viable paths, and then we use the best paths available, which means they're not necessarily optimal, but we need to keep everything going. And interestingly enough, packets that mimic ants have some really good and positive properties from the point of view of security. So when you come to encryption and authentication, there's some really nice properties about this. So what we do, we can actually compute feasible routes subject to the quality of service constraints, which are determined by the type of data traffic to be routed and the reliability of the available links. So the idea is, when searching for a feasible route, these packets, which with a particular structure and carrying particular information we call ants, select their next hop when they arrive at an intermediate node. So when they arrive at a vehicle, but what they do, they use a stochastic mechanism called a state transition rule to look at the information available locally at that vehicle at that point in time. So when it arrives at a vehicle, the next hop is determined based on local information local to that vehicle. It is true situational awareness. Now, in the first paper we published, it's like 14 or 15 pages long in a transaction, and we couldn't really emphasize the situational awareness in that paper as much as we wanted to, because it's important to emphasize it is local decision making. We're not here looking for a globally optimum best route. We are finding good, feasible, reliable routes based on local decision making. And indeed, one of the nice features of these ants is one of the issues actually with these networks that's a real challenge is if a vehicle is tampered with such that it's, if you like, a rogue element in the network, somebody's trying to do harm to others, and we know it happens, all right? What we need to be able to do, we need a notion of intrusion detection. Mutual authentication is not enough in the real world as it is with people being people. And one of the great features of ants, which is in the work that we've submitted for publication at the moment, is we look at the way in which the ants can be used to build up on a vehicle a localized model of the network which you can use for intrusion detection. So there's a whole series of reasons why we might want to look at ants. Okay. So what we do, we choose the best route currently available from a node, intermediate node, to the destination. And if such a route does exist, and sometimes it won't, we provide a reliable and robust routing service doing this. And I'm not here to sort of give you loads of simulations, but it's been very well tested. So I really think that we need to think, when we think about situational awareness, that we can use this concept for intrusion detection. We can use it for looking at the availability of our communications. We do very well by mimicking nature. And the reliable routes, once they're there, need to be monitored, and applicable countermeasures are needed to respond to route failures. So this is sort of looking, if you like, at the security in the true sense of safe, available, dependable computing. And there is a paper in IEEE Transactions on Dependable and Secure Computing, that's January this year, which is the first half of this work, which is secure and robust multi-constrained quality of service routing aware algorithm for vehicular ad hoc networks, which was very well received. We do the mutual authentication using elliptic curve cryptography. So those of you that are into crypto, it's simply too slow to do it using RSA. So regrettably, you have to resort to elliptic, and we know there's issues around elliptic, those of us in the area. But we use that. We can also guarantee privacy, because we change the keys very frequently. We've tested the times that it takes to do this. This is all possible, it's all perfectly viable. Where we're at is we did extensive simulations for motorway traffic. It seems to be absolutely fine for that.